Hey guys, welcome back to the shop. Today I want to talk about ladder logic and electrical diagrams, specifically for machine tools. And I wanted to discuss how to read them, what the symbols mean, and how to make sense of what's going on in the diagram from a troubleshooting standpoint. So this is probably not going to be a very action-packed video, but this is the kind of information that you really can't get unless you have access to, an old timer who has a lot of experience. As far as I know, there's no books or, classes that you can take to really teach you how to read the diagrams. I took a class on RC circuits when I was in college, classes on controls, and I still had no idea how to read these diagrams. And the only way that I actually learned is, a guy kind of took me under his wing and showed me for free out of the kindness of his heart. And I'm hopefully going to return the favor here. This is a diagram, a sticker off of an Amata HA250 automatic bandsaw, and this basically explains all the logic that makes the automatic systems of the saw work. So today, in modern times, we would use a PLC or a CNC control with a built-in PLC in order to do all the logic. But in the old days, before they had computers, what we used is this is a relay, and this is what they call an ice cube relay, I guess because of the clear plastic shell. But basically all this is an electromagnetic coil, and the electromagnetic coil moves some contacts, these little levers inside. I don't know if you can see it. So there's the little lever right there, and it's either normally closed or normally open depending on the action of the coil. So these two pins right here are for the coil. This is a 24 volt DC relay. That's the most common relay that you're going to run into. In this case, there are only two sets of contacts, here and here, and basically the top is normally closed, the bottom is normally open. So same here, normally closed, normally open. So you basically get one normally open or closed circuit over here, one normally open or closed circuit here. So it's two circuit relay with one coil. So this is another kind of a relay here. This is a timer relay, and it basically functions exactly the same as a normal relay, except that it has an adjustable timer here. And typically these can be set for several different functions, but the most common is a time on delay, where the coil is energized and then the relay takes some amount of time in order to actually contact, or a time off delay, where the coil is de-energized but it takes a certain amount of time for the contacts to actually open. So the coil holds after it loses charge to the coil. The contacts hold after it loses charge to the coil. There's other functions that they can do, but that's the most common. Okay, so this is a drawing, a really rudimentary drawing of some logic, and over on this side here I've kind of drawn out what the various symbols mean. So these bars here represent a contact that's normally open, and that's a contact on the relay. So that's this side of the relay. This represents a contact that's normally closed. So this symbol here would normally represent a capacitor, like on an RC circuit drawing or a circuit board drawing. But in the ladder logic system, they typically use this symbol for a contact, like basically a switch. And then a round circle like this typically indicates a coil. Sometimes it's drawn as a box, and I think the Mori Seiki drawings are that way. I'll show you that in a minute. So this would represent a switch, like a push button switch, that has a momentary contact. So that means that it only contacts basically when you either push the switch or release the switch. So in this case it's normally closed. So when you push the button it opens, In this case it's normally open, so when you push the button it actually closes. And then this is a symbol for a light. So in the ladder system you typically have bars along either side, and one side, typically the right hand side, will be 0 volts or ground, and then this side will be some positive voltage. So in this case it's positive 24 volts for our example. So in the simplest circuit, basically power can come from the 24 volt side here. It goes through this contact when the coil is closed and causes this coil C3 to be powered. So if we have two contacts here, C1 and C2, that are both able to give power to the C3 coil, this is basically the representation of a logical OR. So basically, if C1 or C2 is closed, we get power to C3. Now, in this line here, you still have C1 and C2, but this time they're in series instead of in parallel. And so in this case, you would have to have C1 and C2 in order to get power to C3. So this is a logical AND. Now, this next circuit right here is extremely common in machine tools. So this is a parallel circuit, so it's an OR, but this is what's called a latching relay. So when we get C1 contact closed and it energizes C3, this right here is the contact from C3. So whenever C3 coil is energized, contact C3 is closed. So basically that means that it's self-powering or latching. So I'll try to show kind of a basic circuit down here that uses a latching circuit. So this is a push button normally closed switch. This is a push button normally open switch. So if we wanted to, we could basically label this switch on and this switch off if they were on a control panel. So what happens in this circuit is when you push the on push button, you close this switch. That provides power to the light, which is represented as I1, and that also provides power to the coil C3. So basically, if C3 is a relay, it closes C3. That in turn closes this contact C3 and latches both the relay and the light on. Now, in order to turn off this circuit, we can push this push button 1, PB1, which is the off button, that opens this switch and basically kills power to both the coil and the light, and the circuit's basically dead. So that's the way that these kind of components can be arranged together in order to give you some logic. Okay, so let's take a look at this schematic for this Amata bandsaw. And this is a good example because it's very compact. So basically the entire schematic for the whole machine is on this one page. So if you look here, you have L1, L2, L3. That's your incoming power. And if you see these kind of curved lines right here that are all connected together, and it says CB, that's a circuit breaker. So that's your main overcurrent protection for the machine. It's also kind of the on-off switch. And then you see you got a ground right here. So the first thing that happens is two of the phases, L1 and L2, go into a single phase transformer. And X1 and X2 come out of the transformer and they create the voltage for the logic. And it looks to me like this is probably a 110 volt circuit for the logic in this machine. And that's pretty common for older machines. Nowadays everything pretty much runs on 24 volt DC, but in the old days, yeah, 110 volt AC was pretty common for this kind of application. So you can see also that the three-phase power comes over here and it goes through MS and MH, and these are contacts, but those are like large contactors, motor starting contactors basically. And then you see this squiggly line here, OLS and OLH. Those are the over temperature, over current protection for the motors, what some people call heaters. And basically that's the thermal protection for the motor winding. So if the motor gets too hot, it's under too much of a load, these are going to open up and basically kill the motor. There are no fuses here. They must be protected by the main circuit breaker. So the circuit breaker protects the wire. The heaters protect the motor. Okay, let's talk about some more of the symbols here. So you can see there's a push button switch right here, just like what I drew out on my sheet. And then FU, this is a fuse, the way that they've drawn it, I'm sure. You see this kind of dashed line right here. That just represents that two things are kind of mechanically connected. So in this case, WL is probably a light that's actually associated with this push button switch. So when you push this button, the light probably comes on inside the button itself. So here's another scenario here. So see this switch right here? This is a normally closed switch, but it's connected by a dashed line to this switch here that's normally open. And then it actually is connected down here to the very bottom to another PB3 switch that's normally open. So the dashed line means that all of these things are mechanically connected. So what that means is that this switch probably has 3 poles, and when you push the switch, one pole opens and the other 2 close all at the same time. So that's the kind of the magic there with that dashed line. Now if you look at this symbol right here, this is a physical switch. So LSC I'm sure represents a limit switch. So that probably is like an over travel switch or end of cycle switch of some kind. And then if you look here, this symbol is a normally closed contact. There's a normally open contact, normally open contact. And then if you look up here, these circles with the lines on them, those are lights, so indicator lamps. And you can see this GL indicator lamp is connected to the PB2 push button by this dashed line. So again, that probably means that this light is going to be illuminated anytime you push this switch. So you can see here, here's your MS coil right here, and that's going to be this MS coil right here is what controls the MS contactor for the main blade motor. So that's what basically turns on the saw. So you can see if we follow the logic here, in order for the saw blade to run, it has to get power somehow from this side of the schematic, from 1, and go connect a circuit to 2, which is the ground side. So there has to be a complete circuit. So we can look at this side of the coil and see that there's really only one path for it to go from this side of the coil to the ground, and it has to go through this OLS and OLH, and these are represented by these X's, means that these are normally closed, whatever OLS and OLH are. So anytime that those were open, that would kill the motor. And I think that we can remember that OLS is the heater. Yeah. So anytime that these heaters open up, it basically opens up the path to ground for the MS contact. So that basically means that anytime that the heaters trip out, that the contact's going to open. So looking from this side, see that we get power to MS from this terminal here called 7. So 7 probably represents the wire number. And now it's going to get confusing because we have 1, 2, 3 different paths for power to come through. These are parallel connections or logical OR connections. So if R1 is pulled in, it gets power to 7. If R5 is pulled in, it gets power to 7. If this auto manual switch is in the right position and R7 is not open and MS is closed, that's basically the latching relay. So I guess if you're in the auto mode or manual mode, this is how the circuit can latch itself and hold the MS coil in. So that's exactly like the example that I showed. So probably what happens is you push a button and R1 comes on. It turns on the MS coil. The MS coil closes and latches itself, and then basically the motor is going to stay on until this limit switch gets made. That's probably the bottom of the blade travel limit switch. Or this AMD relay opens. That's probably some kind of a safety relay. So that would kill power to it as well. So that's basically how any of these circuits will work. So you can look, there's more symbols here that are relevant. So this kind of squiggly line right here, SOL1, that's a solenoid. So probably that's a hydraulic solenoid, meaning it's an electric coil that actuates a valve. And you see it says lowering right here, so that's probably for lowering the blade. So you see along the left hand side here, there's all these numbers, 1, 2, 3, 4, da 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 da. Those are the line numbers. So each number corresponds to a line of logic. Now if you look over here on the right hand side, where it has all these numbers, 6, 7, whatever, that's basically a reference. So what that means is that if you come over here and you see 6 and 7 are going to be line numbers where this coil can be found. So if we go to line 6, we see that, yep, there's MS right there. If we go to line 7, we see that, yep, there's MS again. So the numbers over here are a reference for where the contacts from this coil can be found in the schematic. So let's go look at another more complicated example. So if we look at R1 right here, so you see it has all these different places where it's referenced within the schematic. So let's look at line 4. Line 4 is here. Yep, there's R1. Line 10, we go to line 10, look, there's R1 again. Line 32, further down, we look at line 32, come over, look, there's R1 again. So this is basically how you navigate the schematic. So once you find the coil for the feature that you want, you can use these numbers right here to quickly navigate within the schematic and find where it's basically doing the work. Okay, so we're looking at another electrical schematic. This is for a Mori Seiki SL20 lathe, CNC, and everything's the same, but it's drawn totally differently. So R, S, and T right here, that's your incoming power. Instead of L1, L2, L3, they use R, S, and T. And then this symbol right here represents your main circuit breaker. This is a transformer right here. They don't really tell you what it does, but I would guess that it's a control transformer of some kind, because it's single phase is how I know that. Z1, I'm not sure. That could be a line reactor or a filter. I don't know. Now this thing here, it says Unit 1, but it says CIMR MT3 7.5K, so I know that's the spindle drive. This is a Yaskawa number. CIMR is always a Yaskawa number, very common. So I know that these connections right here are for the spindle drive. So you can see all the action that's going on with this spindle drive. So RS and T, and then E is the ground. This is your main power coming into the spindle drive. It comes right off the main breaker. And the spindle drive has its own built-in circuit breaker, so you don't have to worry about overcurrent protection on that. These here go out to the fan. Then U, V, and W are your connections to your spindle motor. And then it has these extra connections, CC, CR1, CR2. That's a they call it spindle coil change, but basically this is a Y delta motor. So it's a 2-speed motor, and the drive automatically changes from Y to delta on the fly. This thing says thermal guard. That's a thermistor to shut down the motor in case it gets too hot. And then they say pulse generator, but that's basically just the feedback encoder. So there's +5 volts and a ground to the encoder, and then A channel and B channel. So there's an A positive and an A negative, a B positive and a B negative. So I was going to show you this one because it's a real simple circuit that kind of explains several of the things we were talking about. So this is the logic to turn on and off the chip conveyor, either forward or reverse. So you see this side over here is the positive side, and this is the ground. So it's trying to get a complete circuit from here to here. And then KM34 and KM134, these rectangular boxes, that's the coil for a relay. So if I go to the machine, I can find this KM34 and KM134 as physical relays, and that's what controls my conveyor. This machine is fairly old and it doesn't have a PLC that can do this kind of amperage. Today, it's very common to find a PLC that can switch 5 amps, but in this machine they actually use relays. So you see what's going on here. The machine has some power coming in here. XS106, that's probably a wire number. And then you see this kind of goofy looking thing here. This is actually just a switch. And you see it's connected by this dotted line. So it has a forward and a reverse for the switch. And it basically implies that like the middle is off on both of them. And then if you flip it one way it's reverse and the other way it's forward. So that's kind of like a mechanical interlock within the switch. But then I'll show you there's an electrical interlock too. So it goes through this wire, and let's say we're turning it on forward. We flip the switch to forward. We get power at the KM34 coil, and looks like there's a capacitor and a resistor here just to filter some noise or whatever out of that. And then it goes through, this is probably some kind of a safety switch, like an e-stop switch, and then out. But if you look, it has to go through KM134, which is a normally closed contact. So if you try to turn the conveyor on to forward, but the KM134 coil was on, this contact would be open and it wouldn't be able to open turn on KM34. So this is an electrical interlock and a mechanical interlock within the switch. So that's what's going on there. Alright, let's talk about something a little bit more advanced. This is a list of relays, timers, limit switches, buttons, control features, etc. for a Divlig boring mill. It's a boring mill, but it has some kind of cool features. It has a positioning system where it basically you can set up a stop and the machine will come up to the stop in rapid and then back up, go to a creep feed, come back to the position, lock itself down, and it's extremely repeatable. And all that stuff is controlled by relays. These machines were designed in the 40s, long before PLCs. So if you open the cabinet on a Divlig, you're going to find probably over 50 of these, I ice cube relays like this controlling all the logic, and then you'll probably find another 20 or so timer relays. They're actually much bigger than this one. Allen Bradley timer relays that control all the timing. But this page right here tells you the function of all of them. So like for example, CR1 is a relay, horizontal and vertical travel limit relay. So you know, it just goes on and on about the function of these things. And then this page shows kind of like the larger components of the electrical circuit. So here's your spindle motor, the motor for moving the platen in and out, which is like your W axis. The feed motor. The Vligs are really weird. They basically only have one motor that does the feed both horizontally and vertically of the spindle, and then they're all done by the same motor, but they shift they use like a hydraulic pump to shift a clutch to decide whether it's vertical up, vertical down, horizontal, left or right. Don't ask me why. And then this is another fun one. So this motor right here is both the spindle bar rapid motor. So basically that means a quill feed in and out rapid motor. So, and then it's also a pump. So when the motor turns one way, it does the rapids for moving the quill in and out. And then when the motor spins the opposite way, it runs a pump that shifts the pre-select gearbox for the spindle speeds. So again, they tried to like share these multiple functions over the same motor. It's super complicated. Let's see. That's your power drawbar, hydraulic pump, coolant pump, yada yada. And basically, same deal. There's overload heaters here, and this spindle motor is a Y delta motor, so it has 2 contactors, and then it has forward and reverse. So there's actually 4 contactors for the spindle motor. Anyway, but you can see all these pages of logic. I think there's 4 pages that describe just the logic for the spindle and the feeds and some of the automatic cycles that it's capable of. Yeah, here's the last page here. So yeah, this thing is extremely complicated, and it's all done with super unreliable relays. Alright, I'm going to give you a little example of some issues that I ran into on one of these Vligs, and just how complicated this type of logic can be. So this right here that I've just drawn out right here is kind of a flow chart of the things that have to happen in order for the spindle to start on a Vlig. It's not as easy as flipping a switch. These things are extremely complicated. So the prerequisites for the spindle to start is that here's the spindle start switch right here. It's a push button with 2 contacts, both normally open. And you have to have power over here on this side of the switch in order for anything to work. And that means that limit switch 14 needs to be closed. That's just like a safety switch, it's normally closed. And then this CRMS has to be closed. So you see CRMS up here, this is the E-stop switch or E-stop relay. And so all these different things here that are all in series, those are different things that cause the machine to go into E-stop, including the master stop or E-stop switch. So all these things have to be closed in order for CRMS coil to come in and basically close this switch and provide power here. So assuming that we're not an E-stop, here's what happens. So we push the spindle start button. It sends power over here through this limit switch here into TR15 and TR10. Those are timer relays, and basically I believe those are time off delay relays. So that means that once the coil is de-energized, they remain closed for maybe 1 or 2 seconds depending on how the relay is set. So once those 2 contacts or timer relays are started, this TR15 right here is going to close, and that's basically going to latch the the CR31 coil on. CR31 is right here. As soon as it's turned on, it allows power to go through this way, through the spindle jog switch, which is closed, over here to some of these other relays that aren't really used very often, but it does turn on CR5, and CR5 is right here. So this is going to be closed, and then TR15 here, this is a normally closed contact. On the TR15, that's going to open up, so that's going to prevent the spindle from running for right now. Now, once TR10 timer relay starts, that's right here, it's going to allow timer 13 and 14 to start. Once timer 13 starts, timer relay 13 starts, it comes down here and switches this on, and it turns on this BRRC coil. So BRRC is a pump, and this DeVlig has a pre-select gearbox, so that means you can turn the dial to whatever gear you want, and then when you just push the spindle start button, the machine automatically switches the gear for you through hydraulics. So this BRRC is the pump that shifts the gear. So it turns on this pump, and the pump is going to run until it gets to 300 psi, and when it gets to 300 psi, it's going to trip out this switch right here, LS15. And when it trips out this switch, it's going to turn off TR15 and TR10, which in essence is going to turn off the pump after a time delay, and it's going to close this contact right here after a time delay. So let's say it's like 1 second, so it waits 1 second, and then it closes this contact right here, and then CR5 is closed, so it allows power to go through here to this switch right here, which is the forward or reverse switch for the motor. And then depending on whether you're in forward or reverse, it's going to close SRC or SFC. That's the forward or reverse contact for the motor. Now, once those close, it's going to close this SFC contact right here, and that's going to pull in SSC. So SSC is the Y contact for the motor. So in order for the motor to start, we need forward or reverse, and we need either Y or delta. And it starts in Y and shifts to delta. So SSC comes on and turns on the motor for the first time. So now the motor's running in Y, and it has started this TR1 timer. So once the motor starts turning, this down here is what's called a plugging switch. So the plugging switch basically turns itself on anytime that it senses rotation of the motor. You can think of it kind of like a centrifugal switch. So anytime the motor is running and this plugging switch is active, it's going to turn on either CR30 or CR30A. And the next step, once this timer relay TR1 hits its limit, it's going to open up, and then the motor is going to actually shift into SDC, which is the delta coil, and the delta coil requires CR30 or 30A to have power. So you need the plugging switch to be on before the motor switches to its delta setting, and then once the motor switches over to delta, it'll continue to run until you hit the stop button. So yeah, all these steps right here have to be met in order for the spindle to actually start and run. And that's not the only things that are involved in this circuit. So what happened on this job is that I went out to work on this machine. They couldn't get the spindle to run. And what I actually found is that a couple of these timer relays were bad. TR13 wasn't working, so the pump wasn't coming on, or it was coming on erratically. But the biggest thing I found is that this CRBF right here, switch, was actually turned off. And that's an automatic bar feed cycle switch. So what happened is somebody came along and flipped on a switch for the automatic bar feed, which is never used and nobody knew that. And when that switch is flipped on for the automatic bar feed, basically the spindle is unresponsive unless it's in the automatic bar feed cycle. So it probably took me 2 days to find out that somebody had flipped that switch on and that the timer relay 13 wasn't working correctly. So this kind of stuff is extremely time intensive. But all the information that you need to make that thing work is here in this diagram, if you can understand it. Okay, so we're out at the control for this Mori Seiki SL20. This is a Yasnac LX3 control. The panel's a little dirty, sorry. I wanted to show you how to use these, the wiring schematic with the I/O functions of the control as far as troubleshooting. So if we look at a page in the control, or in the schematic like this, we see some descriptions along the side. So like coolant pump off, coolant pump on, mode select, yada yada. And you see right here, this top rung is positive 24 volts. So positive 24 volts going out here, and then it goes through some various switches and back into the control. Now these arrows, goes through some switches here and then back into the control. Now these arrows right here are pointing out of the control, so you'd think maybe that's an output, but you can't trust the direction of the arrows. That would be too easy. These are inputs, I'm sure, because it's taking the 24 volt source and going back into the control. So if we go to the next page here, we'll see some of the things like block delete, dry run, optional stop. And you see there's a number associated with them. So like optional stop is 1019.5. So we should be able to go to the control and monitor this 1019.5. So the way we do that is just go to the diagnostic page, and you see all these addresses along the side. So the one we want is 1019. Hit the cursor down. So here we're on 1019, and then it's going to be bit 5, which is this one here. So when I hit optional stop, yeah, we see bit 5 come on. When I turn optional stop off, bit 5 goes back to a 0. Now, you notice also that this optional stop has an LED that comes on. We should be able to find that in the schematic, because the LED is probably controlled by the control itself. So let me see if I can find that real quick. Here it is. So if we look at this page right here, see there's optional stop right there, and it says LED 15. So there's a bit associated with that too, 1118.3. So if we go back to our diagnostic page, 1118, cursor down, and then if we monitor bit 3, we should see it come on as well, and it does. So that's the way you can use the diagnostic bits to troubleshoot inputs and outputs. So I wanted to show you, this is the inside of the control cabinet for that Amata bandsaw, and you can see it's extremely neatly designed, but all along this side over here are the relays, but they're actually contactors. So you know, these are able to withstand some higher voltage, and then the ones down here that have the knobs, those are the timer relays. And this is a transformer right here, and then along the inside right here you can see the main motor contactors, and then down at the bottom right here, these things with the dials on them, those are the heaters for the motors. So that's your temperature protection for the motors, and they're variable setting heaters. And then if you look at the black box all the way at the back, that's the main circuit breaker for your incoming power. So that's a scary looking schematic, but this is an extremely well designed and well thought out cabinet. And this machine's been working for 40 years without issue, and I don't anticipate it having any problems anytime soon. So that's going to be it for this video, guys. Thanks for watching. Hopefully it wasn't too boring, and this kind of information that you just squirrel away, and someday you will need it, and when you do, it'll really save you. We'll get back to something with a little more action before too much longer.